Hi, my name is Brett Owers. I'm a full stack developer and AI consultant, and today I'm here to help you expand your vocabulary in the AI space by teaching you the difference between determinism and stochasticism. These words are important if you want to begin integrating AI systems into your workflow. A simple example to demonstrate stochasticism is when you ask a chatbot to perform a particular operation, and then later on maybe you ask it to do the same thing again, and it does something different. That's stochastic. Why is that stochastic? Because you performed the same operation, yet you got a different result. A perfect example is an AI model trained to predict a potato harvest yield. In a stochastic system, the prediction is not a promise. It's possible to train models to predict yields for your potato farm. That said, those predictions may not line up with reality to a T. There's a certain level of randomness that goes on, such as the weather, pests. That prediction is likely going to be different than the actual yield. Being able to articulate when the AI did good and when the AI did bad is going to be key in your AI integrations. If you're working with a consultant and they don't know when it messes up and they don't know how it messed up, it becomes very difficult to make improvements on that system. Another example of stochasticity is storage humidity over the season. The actual humidity can vary quite dramatically over time. An important thing to understand here is this idea of a normal distribution. When you have enough data points, patterns can start to emerge. Take storage humidity over a season, or temperatures throughout June in a given region. We might say that the average high temperature is around 81 degrees, while the average low temperature is around 54 degrees. But those values are not the actual everyday temperatures. They are averages of the extremes. The potential is endless with AI, with the things that you can train it on, but the reality is a lot of these systems are stochastic in practice. Oftentimes the goal of AI is to start to bring a level of determinism into stochastic systems. This is useful because if we can predict demand for our potato farm next season, then we'll be able to plan accordingly. In almost every industry, humans are working tirelessly to try and introduce determinism into a stochastic reality. We want more predictability. We want to know if a particular trucking route is going to introduce a certain amount of defects into our potatoes. I would argue that it's preferable if it was known that a particular trucking route introduced a consistent amount of defects after every trip versus a trucking route with an enormous amount of variance where you can't actually predict how many potatoes are going to get to the final destination without being tremendously defective. What I'm arguing for is introducing more determinism into our systems. Thanks to scientific advances, we're able to adequately predict certain conditions that we can control and their effect on growth rates, the spread of pests. An example of a more deterministic system is the amount of rot you can expect based on the temperature that you're storing your potatoes at. As the temperature gets greater, you can expect less rot. Another example of a deterministic system is if you have a potato sorting machine, you're going to have maybe settings that sort the extra small potatoes into one bin, small potatoes into another, medium into another, large into another, and extra large into another. So because of this, you're going to be weighing the potatoes. And because you have a measurement, you're actually able to predict where those potatoes are going to wind up, or else you have a faulty machine. And you can expect a more deterministic output that at the end of the day, your potatoes are going to be sorted. Think for a minute about quality control. You want to be able to expect and guarantee your customers a certain level of quality. Don't you want to be able to allocate in your mind ahead of time what's going to grow where? Maybe you're not just growing potatoes. You want to be able to predetermine these things. And the best way to do that is to follow models that adequately have forecasted in the past the conditions that the potatoes are going to be growing in and all your other plants. And lastly, another example of determinism is just a schedule. If every day at 8 o'clock you do something, it's predictable and it's not stochastic. Someone who's disciplined and consistent you can consider to be more deterministic than someone who's impulsive and kind of frantic. They would be more stochastic. So when it comes to introducing AI into your systems, what are you looking for? More determinism or more stochasticity? The reality is, when working with AI systems, you're never going to get perfect determinism, but the key is that you're going to converge on a more deterministic outcome, which allows for greater predictability. This reduction of variance actually makes you more deterministic. Your customers will know what to expect from you. Oftentimes why people return to something is because they had a good experience and they're seeking that experience again. Some mumbo jumbo someone might tell you is, our enterprise-grade stochastic neural architecture leverages deterministic embedding spaces to operationalize your KPIs across the data fabric. Now, what does that even mean? I really want to get through to you that you don't have to just take all this jargon at face value. You can break down the words and see if someone's selling you snake oil. These aren't necessarily words you hear every day, so I'm going to use them in a few different forms. Determinism, deterministic, deterministically, a deterministic system, same input and same output. Stochasticity, stochastic, stochastically, a stochastic process, same input, different output. Our shipping route picker is stochastic, same trucks, different routes each week. We made it deterministic for the freezer loads because frozen potatoes can't wait. So now to drill home on like some truly stochastic systems. What we've got here is a simulated dice roll. When you're rolling dice, 1, 2, 3, 4, 5, and 6 all have an equal chance of landing on that value. The normal distribution is a theoretical, symmetrical probability distribution where data clusters around a central average, forming a bell-shaped curve. This means that most of the values are falling in the center, and there's outliers both on the lower end and on the upper end. The normal distribution, as the name goes, is actually quite normal. It pops up everywhere. Each individual roll is stochastic, but the aggregate is predictable and actually more deterministic than you'd think. Every time you pick a new vendor, you're rolling the dice. You don't have data on them. You don't know what they're approaching. You don't know how consistent they are. Finding that vendor that you really mesh well with early on is going to be key. Another example of a stochastic system is random sampling. Let's say you have a field of 100 potatoes and you want to know what percentage of potatoes are defective. If I randomly sample 10 different potatoes, am I going to get the same amount of defects in the amount of potatoes each time? The answer is no. Every time I do it, there's a chance that it's going to be different. However, if we do this enough times, it's going to approach the normal distribution, just like rolling those dice. And using that pattern, we are able to make predictions and understand our data. Another example of random sampling being able to help us make predictions is called the Monte Carlo approximation. Our potato example might be a particular potato was bad and it got planted and it's begun infecting others. If we do random sampling across the entire acreage, maybe we're going to find that there's a radius by which this is happening, and we could root out the bad potato. With a little bit of math, we're able to determine where in the field the bad potato is and which ones need to get dug up. By random sampling, we're able to estimate values that we could never compute directly. Another example of a truly stochastic system is Brownian motion, and you can think of it like the way a potato grows. Potatoes have eyes by which the roots and the stolon come out when they start chitting. So when they start chitting, they start to grow in all sorts of different ways. Now, technically, it's deterministic because if we knew all of the inputs, if we knew all of the soil conditions, how loosely aerated it was, if there's rocks in the way, then we would be able to predict adequately how it's going to grow. It might have to involve us also knowing the genetic composition of the particular potato we're growing. Although this isn't a perfect one-to-one relationship between Brownian motion and the way that potatoes grow, it's a helpful way to understand that certain systems are truly stochastic by their very nature, and others just appear to be stochastic. Another example of stochasticity is the VoIP handoff. Have you ever made a call and you were on Wi-Fi, and then while you were on that call, you left Wi-Fi, and then all of a sudden, it sounds like there's something missing or all the noise gets jumbled in at once? That's a result of you introducing a certain amount of stochasticity into the system. Before you got off Wi-Fi, the messages you were sending were predictable. The moment you got onto the cellular network, it became a little more unstable. So that stochasticity that was introduced when the handoff had to happen is why you get that sudden drop or scratchiness or silence followed by a bunch of words squished into one. Lastly, our final example of stochasticity in this video is the potato stand. At a potato stand, let's say you have big potatoes, perfect potatoes, and defective potatoes. A lot of people aren't going to pick the defective potatoes. So you can actually expect a more deterministic output of which potatoes are going to be taken by random people picking from the potato basket. Now, some people might have a particular size that they have in mind. They like a baked potato, one a day, and they like it a particular size. Other people, they just want the biggest potato that they can get because they can't wait to slather it up with some butter and really indulge. You can expect more determinism when there's those defective potatoes in there. So this is actually an example where stochasticity is not a problem, because if someone's choosing more randomly between a big potato and a perfect potato versus avoiding the defective potato, you would actually, it's more desirable. You don't want people to be picking defective potatoes, but in the first place, you don't want those defective potatoes there in the first place. What I'm trying to do is just give you some helpful ways to understand the difference between determinism and stochasticity. Quite frankly, I think they're both big words, but I use them all the time because when I enter into a system and it's too stochastic, I tend to just avoid it entirely. I just want to wrap this up by saying you don't need a master's in machine learning to leverage AI. You don't need a supercomputer either. What I'd recommend is that you continue watching videos like these so that you can increase your vocabulary and have a better understanding when people try to start selling you these systems.